Okay, today's talk for phase transformation is solidification. So when we talk about the transition from liquid phase to solid phase, we also call the transition is solidification. And we can measure the velocity v of the transition based on the equation here. The first part of the equation talking about the transition from liquid phase to solid phase. And then this second part of the equation talking about the transition from solid phase to liquid phase. You may notice here we have an additional parameter delta G. The reason is for this transition from liquid phase to solid phase, we pick up the processing temperature T, which is below Tm, melting temperature. That's why we have the delta T supercooling parameter produced. We know that delta T is related to the delta G free energy. That's why now the free energy level for liquid phase is higher than that of the solid phase. Then in this free energy change with the different phase for the liquid phase and the solid phase. Clearly, solid phase is more stable because this phase now has the lower energy. That's why we will have the v velocity, which is not zero anymore, to talk about the transition. To be clear, if the delta T is zero, so you will have the liquid phase and the solid phase at the same free energy level. You'll still have the reaction or transition from liquid to solid and solid to liquid. But the two-way reaction or transition have the same rate. That's why overall velocity is zero. Only when you have the temperature below Tm, then the transition from liquid phase to solid phase can be dominated. Now, first we try to explain the detailed solidification in pure metals. Here, the pure metals means when we talk about the transition from liquid phase to solid phase, there's no composition change during the transition. We only need to consider about the thermal energy or heat flow near interface. So let's check the figure on the top right. This is the interface between solid phase and the liquid phase. And this curve gives you the temperature distribution in solid phase. This one gives you the temperature change in liquid phase for different position. GS and GL give you the temperature gradient for solid phase and the liquid phase. At this point, we say both the GS and GL are positive. So now, during the transition from liquid phase to solid phase, this interface will move from this position to, let's say, right, okay, going to the liquid phase direction. Now, imagine you have one local position going fast, produce a tip, going to the liquid phase position. And we know near interface, the liquid phase temperature is just below melting temperature, which means going deeper in liquid phase side, the temperature will be above melting temperature. That's why any tip going to the liquid phase far away from interface will remelt. That's why overall you will get this flat interface. Continue moving to complete the green gloss. However, for some case, you will get this kind of temperature distribution in solid phase and liquid phase. Clearly, in solid phase, the GS still positive, the slope. However, in liquid phase, near interface, this slope becomes negative. What's the reason to produce this kind of result? The reason is during the transition from liquid phase to solid phase, you have the possibility to build up lots of thermal energy here near interface. If the nucleation, if the transition is carried on based on the very high supercooling. Because any transition from liquid phase to solid phase, the transition releases thermal energy. If the thermal conductivity of the solid phase side not high enough to release the thermal energy, then this region will getting hot, getting higher temperature. So which means the temperature in liquid phase side near interface is higher than here in liquid phase side away from interface. Then you can notice now, we know the delta T talking about the processing temperature, okay, which is always below melting temperature. Now, in liquid phase side, away from the interface, the temperature is lower than interface. That's why it is possible for a tip going to the deep position in liquid phase side, because here temperature is lower than the interface position in liquid phase. Then this tip can go in further, also can go into other directions, as long as the temperature in this region is below Tm. Of course, going further to liquid phase side, the temperature will go higher again. That's the reason when you have this kind of temperature distribution in liquid phase and solid phase, you will have the opportunity to produce the grain shape like this. This we call dendritic structure. So one example here is talking about the ice in the window like this. As we discussed before, in this case, now we're talking about the water transfer to ice. So if the temperature distribution or temperature gradient in solid phase and liquid phase both are positive, then the interface growth is flat. However, if the temperature gradient is positive in solid phase but is negative in liquid phase, then in this case you will get the dendritic structure. This is the example again we just mentioned, is the structure you can get from the window event in some north part. Lower temperature, you get this dendritic structure produced because this temperature profile. Now we're talking about the solidification for metal materials in a mold. Sometimes we also call this as the casting processing. Okay, so this mold here normally is cold compared to the liquid phase metal. Now when you have the liquid phase in this mold, so you will get 3 layers produced. First layer we call chill zone. This layer has a very small grain sized structure. The reason for this very small sized grain is the processing starts from the interface between liquid phase and mold. As we discussed before, the mold surface will give you the additional contribution for nucleation. So this is exactly the case for the heterogeneous nucleation. Then you have the benefit from interface to produce lots of grains. That's why very small sized grain produced along this layer. Then when we have the further grain growth, the second layer is produced. Now the second layer we call columnar crystal structures. Basically, along this direction, so perpendicular to the mold wall, you have the highest delta T. and above, below this green here, you have the neighbor greens to block the green growth. That's why the easy way for the green growth is perpendicular to the mould wall. Then you get this columnar structure produced in the second layer. The third part is in the middle. So the morphology of the crystals is isotropic, is an equiaxis structure. The reason for this is again based on the contribution of heterogeneous nucleation. So you have some particles move from edge to the middle to help for the nucleation. Also, you have some large grains. Now they break to different parts. They can also work as seeds to help for the nucleation in the middle part. That's why overall you have these 3 layers produced during casting processing. So that's why here you have 3 layers, okay? Layer on the edge, layer in the middle, layer in the center. You can modify the microstructure based on 3 typical parameters. One we call alloying content, second we call pouring temperature, third we call cooling rate. Now, start from the picture in the middle. If you have the higher alloying content, you will get more chance to produce this structure, lots of grains, anisotropic. The reason is this alloying content can work like particles, can work like impurities, help for the nucleation, specifically help for the heterogeneous nucleation. That's why you get this structure. In contrast, pouring temperature higher, going this way. Reason is pouring temperature higher, you have more chance to melt particles, to melt these impurities. That's why the contribution from impurities or additional particles will be dramatically decreased because they will be melt. That's why you transfer the structure from the one on the right to the one on the left. Cooling rate. So cooling rate higher, you have the higher delta T. So higher delta T, you get the more chance for this second part, columnar structure going quicker to dominate the morphology of the final structure. The figure on the left here shows you one example for aluminum materials based on the casting processing produced product. You can see there are 3 layers roughly, and this middle layer is clear. Okay. Also, you may notice on the top part there is a material missing. The reason for this is during the phase transition from liquid phase to solid phase, which is linked to the shrinkage. Same material, same mass, liquid phase has higher volume, solid phase has lower volume. That's why along this part you have the transition completed, finished. There's the middle part when it transfers to solid phase from liquid phase. There's not enough material to fill the gap, fill the air, fill the space. That's the reason we have this part. Then for the typical steel company processing, you will produce much large-sized ingot like this. Okay. Now we move to the topic solidification of alloys. So the main difference between pure metal and alloys is alloys you have composition change during transition from liquid phase to solid phase. Here the example is copper nickel alloy. So you can say in this phase diagram, point A, you have the composition based on the 35% of nickel. So now, if we decrease the temperature to point B, you will have the 2 phases produced. Liquid phase plus alpha is solid phase. When you further decrease the temperature to point C, now you still have 2 phases, liquid phase and solid phase. But what's difference here is the solid phase composition is 43%, and the balanced liquid phase composition is 32% nickel only. Okay, so their overall concentration, or we call composition, is 35 nickel. But now in two-phase region, either liquid phase or solid phase, they are not at this starting composition. So when you go to point D, you can see most of the phase already transferred from liquid phase to solid phase. Okay, and solid phase is very close to the composition of the liquid phase beginning, so 36. The liquid phase is still lower, 24, because the composition change for liquid phase follow this line, and the solid phase composition change is follow this line. Then when you go to point E, all the phase now transfer to solid phase, alpha phase, and also the composition is also linked with the beginning, the liquid phase composition, 35 weight percentage of nickel. This processing is possible only when you have the very slow cooling rate. Okay, so we say the diffusivity in liquid phase and solid phase both are high enough to enable you get the final composition match the beginning composition. But what you can remember is the solid phase concentration always higher during the transition. Okay, beginning at 46, then 43, then 36, finally 35. This can change to 35 only if the diffusivity in liquid phase is very high. That's why we say for the real processing, we have the structure of a grain. Either follow the figure on the left here, so everywhere we have the uniform composition, 35% of nickel. If the diffusivity in solid phase is also high enough during the transition to enable the redistribution of the atoms in solid phase. However, the real story in many cases is like this. You get this chord structure. So basically the center of a grain have a higher concentration than edge of a grain for this system. Because beginning you have the 46 weight percentage of nickel, and final layer you have much less concentration. This is the structure you can get for some alloys, because during the transition from liquid phase to solid phase, you have the limited contribution based on the diffusivity in solid phase, which will provide the final structure like this. Now let's go to deeper, try to understand more details. So this is the phase diagram, binary phase diagram. Temperature changes with the concentration. We mark as C. The beginning concentration is C0 in liquid phase. When you decrease the temperature, go to this level, in two-phase region, you have two compositions. CLS is the composition for liquid phase. CSL is the composition for solid phase. They are balanced. So now let's say we draw a figure showing, okay, solid phase side, liquid phase side. Then we compare their concentration in terms of the distance change. This is the interface between solid phase and liquid phase. You can notice the solid phase composition is CSL here, which is on the left side of C0, that's why it's below C0. However, CLS is the composition for liquid phase, which is on the right side in the phase diagram, which means CLS concentration is above C0. That's why we have this figure. Here we also introduce one parameter K, we call the partition coefficient, which is the ratio between the solid phase concentration divided the liquid phase concentration. So CSL, this one, solid one, divided the CLS, liquid one. Normally we pick up the phase diagram like this way. That's why K is less than 1. So we still use the same phase diagram, but now we pick up more temperatures to give you the detailed information. Let's say the starting composition is C0. When we go to this temperature, just below Tm, then you will get a solid phase composition here, okay? And they have balanced composition in liquid phase is here. So clearly the solid phase composition is here, below C0, okay? Then when you go to T1 temperature, then the local solid phase composition now is here, C1SL, so it's here, okay? And then the balanced liquid phase composition near interface is C1LS here. You may notice I changed my words. I said local composition only. It is true because in solid phase part, the beginning composition is C0SL, this one, which is below C1SL. That's why we have this curve, okay? So the composition in solid phase continue increasing. Same thing, the liquid phase composition near interface also continue increasing. C0, LS, C1, LS. And then when we go to temperature T2, which is a special temperature, at this temperature, the solid phase composition more or less is C0. So solid phase local composition is C0. That's the C. That's the C0 level, okay? Now the balanced liquid phase near interface is C2 LS. Clearly this is above C0. So only at T2 temperature, you will get the solid phase composition match C0 condition. That's why this part, okay? In this figure, talking about composition change with the distance, with the interface move. The interface we're talking about is between solid phase and liquid phase. Beginning, you have the lower concentration, then you get C0, and finally you get the higher value. That's why for the solidification of alloy, so you may get the higher concentration along green boundaries. This exactly like this figure. We're talking about some iron-based alloys. The average composition for Mn is 0.58, but in reality, near green boundaries, which is the final part for the solidification, you may get a very higher concentration. Link with the figure on the left side. Now, same figure, also we try to understand more. What is the condition we need to consider further to get the, stabilized composition or stabilized structure? This is the figure we discussed before, okay? And we said at T2 temperature, which is a very stable, very special temperature. At the T2 temperature, you can get the local composition of solid phase match C0 condition. But now, the balanced composition in liquid phase near interface is C2LS. Also, we know this position now is stable in terms of time change. That's why we say, in mathematics, we say at T equals T2, dC over dt is 0. To be clear, the concentration C we're talking about only is based on liquid phase. The reason is the composition in solid phase is already frozen. already stable there. Okay, so for this calculation, we think the diffusivity in solid phase is 0. We also understand the K, the definition is based on the concentration in solid phase divided concentration in liquid phase. Okay, so that is the z direction for green growth rate. If z equals 0, this position, we can find the boundary condition for liquid phase. Okay, then the concentration CLS is C0 over K. Then in liquid phase, far away from interface, when Z is infinity, then the liquid phase concentration is C0. Then we're going further. We say the concentration change with time in liquid phase have two contributions, contribution 1 and contribution 2. The first one here, we say is based on the diffusion, based on the Fick's law. The reason we have this part is, you can see clearly, this is the higher concentration, here is lower. So there's a delta C, different concentration. This will be the driver force for diffusion. This will move the atoms from this peak position to a lower position. That's why we have this part. This is the to decrease the concentration in liquid phase from peak position to a position in liquid phase side. This part talking about what is the reason to build up this peak. Okay, this peak build up is based on the transition. So basically, you can say in this two-phase region, right? During the transition, you always push additional atoms going to liquid phase. So because you have less concentration in solid phase, that's why you can imagine you push the atoms during transition part from solid phase original desired composition to the real composition in liquid phase. That's why dC over dt here you have two parts. Okay, first part is decrease the concentration in liquid phase. Second part is the reason to build up this peak, to move the atoms from left side to right side. This part 1 follows the equation for Fick's second law. Second part, dC over dt, you can say in mathematics, you can write dC over dt like dC over dz multiply dz over dt. Why is that? The reason is we try to introduce one parameter, dz over dt. So this interface move with time, which links with the v, with green growth rate. Okay, the velocity. And we know at this temperature, this condition, overall dC over dt is 0. Then based on this equation in mathematics, we will get a function for the CLS, so the liquid phase composition change with z, with distance. So all these equations is to prepare to get a new equation to link the concentration in interface, near interface. Sorry, the concentration in liquid phase, near interface, change with z, green growth rate. This is our aim. Now, we say we have this same phase diagram, okay? And there is a liquid phase here and a solid phase here. In the middle is two phase. And this part, this line, shows you the boundary between liquid phase and two phase. This temperature we mark as the TLS, okay? Liquid phase and solid phase boundary. Here is Tm. So this line, in mathematics, you can write like TLS equals Tm minus m multiply CLS. This is the concentration change, okay? So what is m? M talking about the slope of this line. So basically, this line, the temperature change with concentration, we can write it in mathematics follow this way. We understand, as we discussed before, we have this figure. So the concentration change with distance. Start with here at the 0 position for Z equals 0. This is the liquid phase side. How about the composition change or concentration change in liquid phase? Follow the Z direction change, Z value change. So C is a function of Z. And now we know TLS is a function for C. That's why we can replace C by Fz. Then you can get this temperature change, okay, with Z. That's why this curve. So now this curve talking about the concentration change in liquid phase in terms of the Z value change. Now we change this to a temperature change with Z. TLS is the temperature follow this line. But here is TLS change with concentration. Here is TLS change with Z. That's the aim. This is the main steps of my physics, and for the all detailed mathematics, I will explain to you in step by step in our PBL class. But here we just focus on the physics. So you can say now you have this curve produced, TLS, and then you can draw a line here. Okay, we mark as red one, real temperature distribution as T. So when you have this TLS, you can have a slope for the Z equals 0 position. Okay, the slope for the TLS, delta TLS over delta T at Z equals 0 position follow this equation. So M multiply C0 multiply bracket 1 minus K bracket multiply V divide KD. M is the slope for this curve. C0 is the beginning, the concentration of the liquid phase. K is the ratio between solid phase concentration divided the liquid phase concentration. V is the green growth rate. And D is the diffusivity in liquid phase. Now we're talking about something we say constitutional supercooling. So basically, the supercooling is linked with the composition change in liquid phase near interface. You may notice I always emphasize the liquid phase. Reason is only the solid phase already stabilized, the composition already frozen. That's why all we need to consider is about the liquid phase. Liquid phase will produce the transition from liquid phase to solid phase to produce new product. Then we say here, when we have this delta TLS over delta Z at Z equals 0 higher than delta T over delta Z, then this is the condition we say for the constitutional supercooling. So you may notice what's the difference for these two slopes. TLS follow this curve. Okay, so short name you can remember is this is the temperature in the phase diagram. Okay, or this is the temperature for the melting temperature, let's say. This T is your real processing temperature. Okay, so you can set up this temperature based on slow cooling or high cooling. We know as long as the processing temperature below melting temperature, you have the transition. You can say within this region, the real temperature, red one, always below TLS. So this region we call super cold zone. So this region you will produce the transition based on the composition's contribution. Another way, if you try to avoid this constitutional supercooling contribution, you need to make sure the minimal slope, okay, is here. So if you change the process temperature slope, move to higher slope, go here, then you can avoid this constitutional supercooling. So when you have the contribution from constitutional supercooling, you will change the interface structure from the flat or planar surface to a cellular surface like this. Okay, if you have the huge contribution from the constitutional supercooling, you will get this kind of broad structure for the green shape. We call this as the dendritic structure. In our PBL2 class, we will discuss the equation here. This is the important equation to explain details for constitutional supercooling. In order to explain the detailed mechanism in constitutional supercooling, we need to understand each parameters in this equation, then understand when we change these parameters, how about the connection with the constitutional supercooling. In other way, we can say in order to avoid constitutional supercooling, what is the option we can change the parameters in this equation? Okay, that's all for today. Thank you.